Hi there, and welcome to Lecture 33 on parametric equations. So this topic is quite a bit different than a lot of the other topics we've been talking about in Calculus 2. But it turns out that a good foundation in this topic that we're going to talk about today will be helpful for Calculus 3. So that's one motivation for doing this lecture. Let me go ahead and get into the material. So imagine you have some kind of curve. So I'm just going to draw some kind of curve in space. It'll look like this, and I'm going to label it C. So imagine a particle moves along a curve, and we're going to call this curve C, like I have in the picture. So allow me to just kind of erase this bottom arrow here. And we're going to say that a particle starts here, and we're going to label this the initial point. And then over some kind of time frame or something, this is the path that the particle travels. And we'll have all these little arrowheads to indicate that this is, in fact, the direction that the particle travels over its life. And then we end up over here. Maybe I can even just say that the particle stops at this point, and we'll call this the terminal point. So suppose you have a particle, and it's moving along this path. So what we do is we keep track of the particle's position on this curve somewhere. Keep track of its position separately in the x and y coordinate through a new parameter, and we're going to call it t as our parameter. So t could stand for time, but it doesn't necessarily stand for time. In other scenarios, it could be just some negative number or something. But what this parameter t, what it does is you evaluate two equations at a specific time t, and it tells you where on the curve you are. So this is going to look something like this. These are called our parametric equations. And x is going to be some function of t, and y is going to be some function of t. So what happens is, for example, if I denote this one as t equals 0, what happens is if you plug 0 into both of these equations, it gives you x0 and y0. It gives you that coordinate where you're at time 0. And then similarly, you can plug in like a 5 or 10 or something like that, and it'll tell you the x and the y coordinates separately of where you are on this curve. So I don't know, let's just say that here is where the particle has managed to get to at t equals 5. So if you plug in 5, then these separately tell you the x coordinate of where we are, so x of 5, and then y of 5. So that's what we're doing. So instead of expressing this curve as a normal function of y equals a function of x, it's harder to do it with a curve like this. So we keep track of each coordinate separately. And that's the idea of what we're doing. So let's take a look at an example where we sketch a curve ourselves. We're going to sketch the curve using the parametric equations. So here's the two parametric equations. The first one tells you the x coordinate and where it's going to be at any given time t. And then same with the y here. This equation right here, this separate one, explains where the y coordinate is going to be at any time t. And we're also going to use arrows to indicate the direction that this curve is moving over time. So how would we do something like this? I think the most basic approach would be you would want to make some kind of table that keeps track of where everything is. And notice for this example, we're just going to keep track of what's happening from time 0 to time 5. So that's the snippet of time that we're interested in for whatever particle this is or whatever object is moving. So what I'm going to do is I'm going to fill out this table from 0 all the way until 5. And then we'll see how our x and y coordinates are moving as we go down the table here. So if you plug in t equals 0 into each of these equations, you're going to get 1 and 0. So what that translates to, if I draw a graph over here now, is, let me label some of these. I'll label this as 1, 2, 3. And then over here, maybe I'll do 1, 2, 3, and then I'll do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So when t equals 0, we start at the coordinate 1, 0. That's what happens when you plug in t equals 0 into both of these. So this is the point where whatever this object is, this is the starting point. And we call this the initial point if we have some kind of initial t value we're given. So this is our initial point. So this is where we're going to start, and then we're going to start moving along a curve that I'm going to sketch out now. If I plug in 1 for t into both of these, you would get 2 and then minus 3 for the y-coordinate if you plug in t equals 1. So you should see what we're doing. Maybe you can go ahead and fill out the rest of the table and also try drawing the curve and see what happens. But I'm going to do it now. So if I plot the point 2, -3, it's down here. So what's happened is we've moved from here to here after 1 unit of time, or whatever t is supposed to represent. And this is the direction we moved in. We started from this point, and we moved down to here at t equals 1. And then let's plug in 2 now. So if I plug in 2, I get 1 plus root 2 for the x-coordinate, and I get -4 for the y-coordinate if I plug in t equals 2. So root 2 is about 1.4. So we would be at about 2.4, and then down here one more unit at -4. So we continue to move down here. So that's at t equals 2. And let me go ahead and fill out the rest of the chart. Now this is 1 plus root 3, and then -3. This one is, if you plug in 4, you get 3, 0. And if you plug in 5, you get 1 plus root 5, and then 5. So just mapping out what the rest of this picture does, at 3, you're at about 2.7, so about here, and then -3. So it looks like what happens is around this point, you start to curve back up. So this was t equals 3. And at 4, you're back up to the x-axis again. At t equals 4, you're at the point 30. So it comes back up here. So the arrows are going this way. And then at 5, finally, you would be at 1 plus root 5, 5, which I guess I'll put that way up here. And this is a rough sketch of what the curve did. So this travels down to here, and then at about 2 or 3-ish, it jumps back up and it starts increasing up here. So this is a sketch of this curve. And the idea you want to take away from this is that what we're doing is we have one variable, one parameter, and what it's doing is that it's separately keeping track of what the x and y coordinate is at each stage. So it just separately keeps track of those coordinates. Let's take a look at this example now. So here we want to eliminate the parameter, and we want to go back to what the original equation is, the original y equals a function of x equation. So we want to decipher what the original equation was if these are the parametric equations. So these are our given parametric equations. So how could I do that? Well, I know x is equal to the square root of t. So what I could do here is I could say, well, y is equal to 1 minus t. However, t is the same thing here as the square root of t squared. So if you notice, x is the square root of t, so I could just plug that in right there. So I get 1 minus the square root of x. So if you look all the way back to the beginning here, I have y equals, this tells me that y equals 1 minus x squared. So if you do some clever substitution in some algebra, you can get back to the original equation that we parameterized, which is going to be y equals 1 minus x squared. And what is that the graph of? It's a parabola. Notice here, there's no restrictions on the t other than the fact that t needs to be at least 0, right? Because you have a square root. So that's really the only restriction that we see on here. So I have a parabola, and my initial point is going to be when t equals 0. So let's try to take a look at what the graph would look like. So we do know what the graph of, well, we should know at this point what the graph of y equals 1 minus x squared looks like. What I'm going to do is I'm going to draw it as a dotted version. So I'm gonna put the point up here at 1. And recall that the parabola, if it's 1 minus x squared, it goes upside down like this. But I'm not technically drawing it in yet. I'm just drawing kind of like the ghost of the parabola, OK? So this is what it would be if you drew the entire parabola. But don't imagine that's not there. It's just for us to see what it would be if I drew the whole picture. But now, let's take a look at what's going on for some of the values of t. So when t equals 0, if you plug in 0, what coordinate do you get? Well, you get 0 for the x coordinate. And if you plug in t equals 0, you get 1 for the y coordinate. So this right here, this is my initial point on this curve. So right here at 0, 1, this is my initial point. And I'd also like to have a sense of the direction of where we're moving. So let's increase the time a little bit. Let's plug in maybe t equals 1. So if t equals 1, what do I get? Well, if I plug it in, I get 1 for the x coordinate and 0 for the y coordinate. So after 1 unit of time or whatever we're measuring has passed, we've moved down in this direction. That's because we have the sense of the passage of time. As I'm increasing the t, we move from this initial point to this new point here. And you can see that we continue to fill out the right side of this parabola. So let's just plug in, what would be a good number? 4. If you plug in t equals 4 into the equation, I just picked a nice number, right? If you square root it, you get 2 for the x and then negative 3. So here at 2, I have 1, 2, 3. Here is where I've gotten to. And this goes in this path forever. This will go down all the way. So what this accomplishes here, this parameterization, is it gives you the right side of this upside down parabola. And you need to take into account the fact that we have a terminal or an initial point here, and then we have no end to this. This goes down forever, right? So that's the path that it's moving in. There's like a sense of a direction on a curve. OK, I challenge you to try this one on your own. So when you're done drawing it, also label the direction it's going as well. And I'm going to go ahead and attempt this now. I'm going to show you basically the trick, what you need to do with cosine and sine here. So let's take a look at this. First, what I'm going to do is I'm going to solve for cosine and sine. So these two equations tell me that y over 4 is equal to cosine of t, and also that y over 5, this is a 5, by the way, is equal to sine of t. So first I'm going to solve for those. Then I want to recall the fact that 1 is equal to cosine squared of t plus sine squared of t. As long as these two angles here match, this is an identity we know. This is the Pythagorean identity. OK, however, that means that if I plug in cosine and square it and sine and square it, I can substitute these in. So what's cosine? It's x over 4, and I square it. And what's this one? This is y over 5, and I square it. And then if I simplify this, I get 1 equals x squared over 4 squared plus y squared over 5 squared. Now this might be a bit of a stretch for you, because a parabola is something that we easily have accessible in algebra classes, and you draw up millions of them. This is a conic section that you might have seen maybe in pre-calculus, and then that was it. You were done with it. But this type of equation, and I'm proud of you if you know this, this is called an ellipse. It's like an egg, basically. It's an egg-shaped thing. It's not quite a circle. It's like an egg. So this is an ellipse. I'm going to show you what that looks like. First is just the ghost version, like the dotted version. And then we're going to fill in the actual path. So if you allow me to, I'll draw it over here. And how do you graph an ellipse? Again, I'm asking a lot for you to go back to pre-calc and think about that. But what you do is you look at the number being squared in the denominator under each of these axes. So for example, you have 4 squared, which means that the ellipse needs to be 4 in the direction of x on either side. So this is 4 units on either side in the x direction. So I'll just write out this one, and it's similar for y as well. So the center for this is 0, 0, because you don't have any value being added or subtracted to the x and the y here. So the center is at 0, 0. And from the center 0, 0, you're going to count out 4 units in the x direction. So it's 1, 2, 3, 4. 1, 2, 3, 4. And this gives us initial points right there and there. And then again, you look to this number, you take the square root of this, and this is our b. This tells us how far we move from the center and the y direction on either side. So this would be 5 in either direction. It's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we've kind of got the 4 points on the outside. That's going to give us our egg shape here. I'm going to do a dotted version of this now. So don't laugh at my drawing, but it looks something like this. OK, and remember, our graph is, oh gosh, I've kind of missed that point. Our graph isn't on the paper yet. That's our egg right there. And now I need to fill in the part that I'm given here. So notice that this time, unlike the other problem, they specified right away where you're going to take your t parameter. So we want to start at negative pi over 2. So let's go here. When t equals negative pi over 2, we need the x and y coordinate. So we can go back to the 2 equations here and plug this in. So when we have negative pi over 2, you get the point 0 for x, because remember, cosine of pi over 2 or negative pi over 2 is 0. And then for sine, we're going to get negative 5. We have 5 times, and if you plug in this, you get negative 1. So this right here, because it's the least value I'm given for the parameter t, this is our initial point. This is where the journey for the particle starts. So we have a sense of that for these. So at 0, negative 5, that's our initial point. And now we need to know what direction we're moving in. So between negative pi over 2 and pi over 2, a good value to pick would be t equals 0. That's an easy value to plug in for t. And if I plug in t equals 0, I'm going to get 4, 0. So that tells us that we move along in this direction. And we're not going to jump off of this curve that I've drawn, because this is the only possible path it could take. You have to stay on the curve here. So we move from here, our initial point, and it tells us we move up here to this point. And then let's keep going. So then if t equals pi over 2, this time I'm going to get 0 again, but I'll get a positive 5. So what that does is from 0 to pi over 2, you continue your journey up here, and you make it to here. So this is the movement. We're moving up in this direction, the counterclockwise direction. And finally, that's the end of the interval we're given. So this is the terminal point. So notice in this case, we had an initial and a terminal point because we had 2 finite boundaries. But for this example here, there was no terminal point. It never stops going down here. OK, so I hope this helped explain what parametric equations are trying to achieve, the fact that they're keeping track of x and y separately to map out the path of something. In the next part of this video, it's very short. I'm just going to give a couple of typical examples of curves and some straightforward ways to parametrize them. So I'll see you for that in just a moment. Welcome back. So now, for the last part of this video, we're going to take a look at, given a planar curve, how would you write your own parametric equations that could describe a path for that curve? So here's my first example. We have y equals x squared minus 4x. So what does that look like as a planar curve? Well, it is a parabola. So if you plug in 0, for example, for this, you would get 0. And then another point you could plug in and also have an x-intercept would be 4. If I were to factor this, for example, I'd get x times x minus 4. So if I plug in 4, I would also have that this intersects here. And then the vertex of this, well, if I did the formula for the vertex, I would have x equals negative b over 2a. My b this time is negative 4. And my a is 1. So I know that x equals 2 is going to be where the x coordinate for the vertex is. And then the y coordinate, I would get that by doing 4 minus 8 would be, 4 minus 8 would be negative 4. So it would be somewhere 1, 2, 3, and then 1, 2, 3, 4. So here's the vertex. So this equation is a parabola. It looks something like this. What I want to do is I want to explain this graph using parametric equations. So we have a really nice way, an easy way to do it for something like this. So if you have y equals some f of x, and what I mean is that it is already solved in terms of x for you. So in terms of x. So here, for example, I have y equals. Everything else over here, the only variable I see are x's. So if you have this special situation right here, all you have to do is this for the parameterization. You're just going to say x is t. So we'll just say x is the time variable. And then y is just, you plug in t for x, and you get t squared minus 4t. And then we'll just say, well, t goes from negative infinity to positive infinity. And that'll map out the entire curve you need. And you'll go in the direction, I guess, from left to right, because that's how x is read. So you would be moving along in this direction. For example, if I plug in 4, I'd be over here and I'd get 0 again. And if I plug in 5 or 6 or 7, I'm moving up this way. So that's the easy one. If you have a function that's already solved for you, y equals a bunch of stuff in x, you can use this parametrization. That is an option. How about for just a particular line segment? So what if you started at 2, 5, and you wanted to end up at 7, negative 1? How would you describe that using two different parametric equations? So I'm going to draw my picture here. So I need up to 7, 1, 2, 3, 4, 5, 6, 7. And I need 5 this way. And I need at least 1 down here. So what I'm trying to do is I'm trying to describe using parametric equations starting at 2, 5. So 2, 3, 4, 5. And I need to end up, I'll call this initial point, IP. We're moving to 7, 1. So I've counted out 7. Here's 1. So it moves, it's a line segment, and it moves in this direction. I need to, I'll say this is terminal point, TP. So I need to write two equations that describe this movement. Now, there are infinitely many ways to do this, but I'm trying to give you the most straightforward one that you can have at the ready, just like for this one. So one way you can do this is you can start by writing the point that you want to start at. So start at 2, 5. And then I need to consider the slope, or like the change in each variable. So x goes from 2 to 7. So that's a total change of what has to happen. The change in x that needs to happen is 5. That's my total change in x. So I need to add to this 5t. And then what's the total change in y that occurs? Well, I start at 5, and I go to negative 1. So that's a change of negative 6. So you have to think about where you started, where you ended up. This is going to give me negative 6t. And now I just need to specify that this whole event from moving from here to here, that occurs after 1 unit of t. So I'm going to say this time that t starts at 0 and ends up at 1. And you can plug things in here to check that I've described this correctly. If you plug in 0, I get the point 25. And if I plug in 1, I would get 7, -1. And on top of that, if you plugged in something like a half, for example, if you plugged in t equals 0.5, you would get 4.5, and you would get 2. And that's supposed to be right in the middle of my line because I'm halfway done traveling. And that's true as well. So this is just one way to do it, but this is one of the most straightforward ways to parameterize a line segment. Last, I'm going to talk about doing it for a circle. So here's the idea for this. We need to have x equal to the radius times cosine of t. And we'll have that the y-coordinate is going to be r sine of t. So you saw a glimpse of this in the first part of this video. We had these parametric equations with some different coefficients, and it turned into an ellipse. So this is very similar, but our ellipse is actually going to be a circle this time because these two coefficients, the r's, are going to match. So how do we do it for this? So this is a circle. This is centered at the origin. So what I'm going to do is I'm going to have this. Our parametrization is going to be 8 cosine t, and it's going to be y will be 8 sine t. And I need to specify my bounds for the parameter. Well, to take one full trip around this circle, what I'm going to need to do is I'm going to need to start at 0, and I'm going to end up at 2 pi. That gives me one full revolution, so I've actually mapped out my circle once. And so if I draw a picture here, I'll just say this is 8 and 8. Let's do a couple points just to make sure that this is OK. If t is equal to 0, my initial point here, the point I would get would be 8, 0. So what I'm doing with this particular parametrization is I'm starting here. And then let's move to t equals pi over 2, which is a little bit farther along in our journey here. So then you plug in pi over 2, you get 0, and you get 4 when you plug in pi over 2 to this bottom one. So you end up traversing the whole first quadrant. And this is what it's going to look like. You have t equals pi over 2 here. Then you're going to go down here to t equals pi. You go down here to t equals 3 pi over 2. And then finally, you'll finish your journey of the whole circle at 2 pi over there. So your initial and your terminal points, they're the same in this case. That you end up in the same spot because it is a circle. So this is just one way to do it. There are infinitely many ways to do this too, right? You can just adjust these. I could have said from 6 pi to 8 pi, or I could have said from pi over 2 to 5 pi over 2, right? I could have just started here and then also did a full circle there. So again, there's many ways to do this. This is just the most straightforward way I could think to parametrize a circle, for example. One thought for you, maybe you can figure out how to parametrize a circle if it's not at the origin. So maybe take your circle and move it somewhere else. Yeah, and try that for different shapes and see if you can come up with different parametrizations. All right, I hope this gives you a good foundation of what parametric equations are, and I hope you got some good practice today. Please send me questions if you have them, and until next time, I'll see you later. Bye.